All right. Next, I will also record this session. Okay, started. Okay. How many of you have gone through the videos of data envelopment analysis? Okay. How many of you? I don't think anyone has gone through the videos of DA. Okay, I see Kamlesh Kumar. Thank you for watching, and Krishna Mohan. Okay. So majority have not watched. So therefore, my request to you all is watch DA videos and come back for next session. We will do DA next week, and after that we will do conjoint. Okay, and we will be solving numerical problems in the next session. And I'll make sure you're ready to face the final exam with regard to DA and conjoint in the coming days. So whatever we do in the live session will be more than enough to tackle the end term exam as far as DEA and conjoint are concerned. My request to you all is please watch DEA and conjoint video. So for next week, watch DEA video. For the week after, watch conjoint and come. So today we will do something different from the routine, right? Uh, so we know we had some assumptions that you already know certain things, but looking at the feedback, we wanted to revise a few topics so that you have better confidence in facing interviews for internships and jobs and so on. All right. Today we are going to do two interesting things. One thing is assumptions of linear regression. How do you validate linear regression model? Second thing is how do you deploy models? Has anyone deployed certain models using packages like Streamlit? Was it covered in some other subjects?
No, not yet.
Okay. So which means this will be a different game for you. Today, we are not going to look at the routine business analytics problems. Today, we are going to slightly deviate and understand two different things. One is how do you validate linear regression? Number two, we're going to deploy a classification model, Streamlit for UI. Yes, yes. Similar to Streamlit, there is another package called Gradio. All right. So we will cover Gradio and uh, validate a linear regression model. So let's get started. Let me share my screen. Right. All right. Is my screen visible? Hello, I won't be able to see you. You might have to tell me. Is my screen visible?
Yes, yes, it's visible.
Okay. Okay.
Yes, sir.
So we are going to do some basic things and then get into the technicalities of linear regression. So as usual, I'm loading a data set into my Google Colab. The data name, the file name is data3.xlsx. It has 200 observations and 5 columns.
Sir, sir, so major part of the screen I'm seeing the participants. This one, can you zoom it out so that?
Sorry, can you repeat? Major?
Yeah, yeah. In the screen, I think more than 50% of the screen, like is we are seeing the
Oh, okay, okay,
participants. Yeah, participants in the session. So
okay.
if we can sort of have a larger portion for.
Sure, sure. Thanks for pointing this out.
Thank you, sir.
I will try doing that, and you will have to give me feedback whether it is better or not. Uh, okay, let me go there. Is it better now?
No, still.
Okay. Okay. Uh, how do I get rid of that? Okay. Let me try something different. Wait. Okay. So now I will make sure that only my okay. Okay. Should be better now. Is it okay?
Yeah, better.
Yes, sir. Yes, sir.
I will also zoom in a bit. All right. So what I have done, I have uploaded a data file called data3.xlsx. We will see what this data3 is about. It has 5 columns and 200 rows. That's all. So uh, these are not real data. I have created this. These are pseudo data. Just for understanding purposes, I have created something called x1, x2, x3, x4, and y. Or your target variable here is y. Your input variables are x1, x2, x3, and x4. So there is nothing that we have done differently so far. I'm just calling x and y here. I'm doing a simple train test split here. I know it is little fast because you already know all these things. That is what I'm assuming. If there are any questions, we can take it up. I'm going to call a simple
Sir, can
OLS
you
model.
tell, sir, can
Hmm.
you tell that X and Y code what you have done there?
Okay, sure. So whenever you have any problem, the best way to understand them is print them and see what is x here. X is a data frame which has only x1, x2, x3, x4. There is no y variable here.
Um,
Similarly,
okay.
if you want to know what is y, just print y and see. It will have us.
No, no, I am not asking about that. I am asking about that colon and then DF column not equal to target. So you have taken only those columns which are not equal to target, or what you have
Yes,
done there?
I have just excluded target from my x. It is df that excludes target. That's all. So
We
these are
are building linear regression model or logistic.
we are building a linear regression model.
Okay, okay.
So whatever we are doing here, don't focus on the coding part because the the purpose of BA is not to teach you coding. We can revise what we have done in BA so far, but let us complete this and come back to that. Okay. So
Okay,
we have
okay.
X and Y here, simple X and Y splitting. I have a train test split. I am building a simple OLS model. What is OLS model?
Ordinary least squares.
That's all. That's all. I am just fitting a model I am building. I'm building an OLS model. I'm fitting it here. And what I'm getting here, what is this constant? What is this?
Intercept.
Intercept,
Intercept.
intercept,
Beta naught,
beta
beta
naught.
naught, beta 1, beta 2, beta 3, beta 4. That's all. And if I plot a summary, if I print the summary, this is what I'm getting. So what are the important things that we need to focus on this?
F
R square,
statistics.
adjusted
R
R
square,
square.
R square, adjusted R square. Okay. Okay. So now tell me, I have a good R square. Okay. I have a very good R square. 90% R square is a decent model. How do I validate the model that I have built is accurate or not? Is it a correct model or not? How do I do that?
By comparing the p-value with the significant value.
The F statistic value,
Yes.
if it is.
So the about the
Somebody
metrics.
somebody told me p value. That's a very good answer. And who told that?
Me.
Okay.
Sabha.
Sabha. Okay. So how do you use p value to understand this model?
Like if p-value is less than alpha, so we say there is no significance. That means the model, there is no significance in the model.
Yeah. So here, what is this x1 here? What does this say? 0.09. So let's say the significance level is 0.05.
Mm.
So what does this say here?
For
Our
this
x1?
particular value, yeah. So it says that it's not. We will not reject the
Hmm.
p-value. This
Okay.
if hypothesis, yes,
So in linear
because it's
regression,
greater.
the way you interpret that is maybe this variable is not significant for the model because the p-value is greater than your significance value. Okay. If you look at x2, it is less than 0.05, but look at x3 and x4, they seem to be okay. But x1,
Mhm.
as you mentioned, it is greater than 0.05. So even if your model, even if x1, let us assume that this x1 is around 0.04, then what you will do?
Then also, like it's p less than alpha, we will
Yeah.
reject the hypothesis and then we'll say that x1 is explaining the relationship. It's actually playing a role in predicting the value of y.
Okay. So what I'm saying here is, so here it is 0.35 x3. it is way more than our significance level of 0.05. You can clearly reject this. Similarly, x1 is also greater than 0.05, right?
Mm.
So now the next step is we need to understand why this is greater than 0.05. What is the reason for
Sir,
this?
sir,
Yes,
I have a small
because
question.
Hmm.
At the very last, there are two values, 0.25 and 0.95. I assume that's the minimum and the maximum. And the value, if that lies within that particular range, we will say that it's a good value for coefficient, right?
Uh, you mean to say this interval?
Yeah.
No, 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 no. It's actually called something like a prediction interval. Let us not get into those things. It will confuse a lot of people. So let us focus on this p-value. So here, what I'm trying to say is you have values that are greater than your significance level. So how do you interpret that? The first interpretation is that variable may not be significant in your model, right? You can exclude that variable. That is one way to interpret that, right? So now my next question is
Sorry,
even
sir, come again, sir. I didn't like. We have this as less than 0.05, right?
no, it is greater than
I
0.05
mean,
here.
here, yeah,
Uh,
okay. This is which means
Hmm.
we have to reject the null hypothesis that it is not significant, which means
Yes.
it is
So
significant.
the classical way is you remove x3 and x1 from your model, and then what you can do, you can build your linear regression again. Is it making sense?
sir, why?
X3 and X1.
Yes,
Oh,
x3 and x1, you can remove them and rebuild your linear regression model and check the model performance. Will that improve or reduce?
how
Will
is
your
X1? So what is X1 here? So 0.09, right?
yes, the p-value of x1 is 0.09. So what I'm saying is you already got a model performance of 0.909, all right, with your x1, x2, x3, and x4. So now what I'm saying is since your x1 and x3 are having p-values greater than your significance level, can you remove x1 and x3 and rebuild your regression model? That is my question. Can you do that?
yes,
And if you do that,
Yes, sir.
what impact it will have on your R
Sir,
square?
why? Sir, why
Model should
we can remove
improve.
it? Because X3 and X4 are, means, those are reasonable values, so we can keep them, right?
What is this
So why we will
Okay.
remove that? Is it due
because
to dependence?
Yes, Madam Saba, I think it's Saba. Can you explain this?
yes, because it's these two variables,
Hmm.
they are, it's a case of multicollinearity, you can say that you
Okay.
can
Okay.
explain this y predict
Hmm.
with the help of the two variables only. You don't need those two. They are redundant variables. They are not
Okay.
playing any significant role.
Beautifully
Now,
said. Multicollinearity. We'll come back to that. But let us stick on to this particular term of p-value. So p-value, what is the hypothesis for doing linear regression?
so,
Reject
so we
H0
need to
if
have the
they are not
p-value.
significant.
Not significant.
P-value
Yes.
less than significant
Beta
value, right?
beta is equal to 0. Beta,
Hmm.
you yes. So here, what are we
Beta is equal
getting
to
here?
0.
You are getting a p-value of 0.35, which is greater than your significance level of 0.05. So therefore,
Hmm.
I am just giving you a simple intuition that since you have a p-value greater than 0.05 in x1 and x3, just remove them from your model and rebuild a linear regression and look at the model performance. What is
Okay,
your model? What is
so
your model performance?
the
It will
bottom line is
increase.
X1 and X3 are not significant,
0.909.
right?
That is what this summary is telling. X1 and x3 are not significant.
Yes,
So
yes.
let us proceed. Let us not get stuck here. X1 and x3, they are not significant. If we remove x1 and x3 and rerun this linear regression, what would be the R square value? Will it increase or decrease?
It should increase.
It should increase. That's a theory
Increase.
that we are looking at. So many people, what they do is, this is how they will go. They will stop with this p-value. They will stop with this p-value. They will say that this is greater than 0.05, therefore I am excluding my x1. This is greater than 0.05, therefore I will exclude x3, and they will build a model in this fashion. So there are certain assumptions that we need to check in order to validate our linear regression models. What are those? You remember these would be, ideally these should have been discussed in your statistics course or the initial course where you were taught linear regression. Did you have a chance to do that?
No, sir.
Okay, no problem. We are going to revise them. Uh, Madam, Sabha madam, you mentioned something called multicollinearity. What is multicollinearity?
Okay, so when we have the explanatory variable,
Mm-hmm.
then when they are correlated, when there's a relation between them,
Mm.
so what happens is that since we need to, reduce the number of features, why we need more features who are explaining the same variable y. So we
Okay.
can
Mhm.
just reduce the number of features who are correlated.
Okay. 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 So to explain this better, we can take an example. Let us say you want to predict how much Virat Kohli is going to score tomorrow, or how much runs he is going to score at the end of his career, right? You are going to predict how many runs that Virat Kohli is going to score towards the end of his career. So what are the input variables that you will take for predicting the total number of for predicting his
Average,
total score?
average of the scores that he.
Okay, so let's even simplify this problem. Let us. Is my Excel screen visible?
No, not
No,
yet.
sir.
No. Okay. Okay. Then let me do it here itself. Okay. Let us predict price of a player in the IPL auction. Right. Let us take some player of your interest. We are going to predict how much this person will be sold for in the IPL auction. Okay. So what are the variables that you will consider?
Scoring
Average
average,
in a
batting
scoring
average.
average,
Okay. Number one is
strike,
average.
strike rate.
Okay. Strike rate. What
Yeah,
else?
we are talking about batsmen only, right?
Batsmen. Let's take us. Batsmen are relatively simpler. Bowling becomes a little difficult.
Then,
Then what else? Hundreds. Number of hundreds.
yeah, we can take in account the experience also, the number of matches the player has
Okay.
played.
Matches. Number of matches. Okay. Next, strike rate. Average. What else you can take? Number
We
of
can take,
fours. Number of sixes.
yeah, number of
Um,
century what that we have taken. Number of times a player has scored zero.
fours. Yeah. Yeah. Very good variable. Okay. Number of ducks. That is called number of
Uh,
ducks. Right. So what happens with all these variables? So don't you think, okay, we can also include another thing called number of 50s.
50s, and that will
50,
be collinear.
okay,
Yeah.
right? So number of hundreds, right? Total runs so far, right? Total runs. So how many features we have taken? So we have 9 odd features. These are not the exhaustive list of features, but this is enough for explaining multicollinearity. So what will happen? Wait, okay. So when average is high, do you think the strike rate will also be high generally? Or when average is high, the number of 50s or total runs, are they positively correlated? When average
Ye-
is high, then total runs
Yes,
will also be high.
yes, yes.
All
I
right.
think average and total runs.
Okay. When number of sixes are high, will the total runs be high?
Yes, sir.
Yes.
When the number of fours are high, will the total runs be high?
Mm. Yes.
So ideally, what is happening is there will be double counting, which will impact the model performance. So when one variable can explain the total variable variance in the target variable, if you are including more number of features that are highly correlated, it has a tendency to degrade the performance of your machine learning model. Therefore, what we do is we do something called check for multicollinearity, right? So what I had done, I have built a OLS model. So next, what I'm going to do is I'm going to test them. I'm going to make predictions, right? I'm going to make predictions using this function called predict on my X test, and I'm going to compute the residuals. The first check that I have to do is check for multicollinearity, for which I'm going to use a package called variation inflation factor. Okay. And this is a package that is available in stats models. And I'm going to check for all the variables that I have. This x underscore train dot shape of 1. This is going to go through each and every variable that I have, and it is going to print something called VIF. So the VIF for x1 is 17.54, x2 is 5.48, x3 is 5.48, x4 is 8.82. So what does this say?
Highly correlated variables.
Okay. So there is a range for VIF. So the range, the ideal range for VIF is around 5 to 10. 5 to 10 of collinearity is fine. And if it is greater than 10, it is highly correlated. Therefore, what does this say? My
X1.
X1 is 17.54. According to this, I should ideally remove X1, build my linear regression model with X2, X3, X4, and then check for my R square, and then check for my P values and make a conclusion. But there are certain problems. So maybe X1 is a more important variable than X2. X2 is a more important variable than X3 and so on. So you need subject matter expertise here, whether to remove X1 or X2 or X3 or X4, right? Maybe X1 is the most important variable. And if you simply get rid of X1 and do your model with X3 and X4, some business people or stakeholders may not be okay with it.
So,
So
but VAF being high for X1,
mm,
it is highly correlated, right? Like it might be
yes,
important, but we can arrive at this with some other variable. So,
yes.
how do we like? Why should we consider X1 as important? Because maybe X3 is explaining X1, right?
Yeah, that is what. So ideally, according to this VIF function, you can get rid of X1, go ahead, do your model with X2, X3, X4 and give results. But if X1 is an important variable, maybe you can keep X1, get rid of some other variable, which is
Okay.
correlated with X1.
Okay.
So for that, what do? You have to plot correlation plots between all the independent variables. See, ideally, you cannot do this model building. The first step is to do exploratory data analysis, understand the data. So since this is not a proper machine learning course, this is just a business analytics course where we are more interested in interpreting the results rather than the modeling perspective. Therefore, we are directly getting ahead and doing all these things. Whereas if you are building a model, it has to start with EDA, which is exploratory data analysis, where you understand each and every variable, look for their distributions, look for transformations, outlier detection, missing value imputation. There are so much. If you even do you can even do a separate course on exploratory data analysis. That's an art. It's more of an art than science. Okay. So according to this, you check for multicollinearity and remove the factors that are highly correlated. Then go ahead, build your models, and then what will happen? Your ideally when you do that, your R square should go high and your P values should be sorted. So what I will do is after this session, I will send this collab file as well as the data. I will give you this data as well as the collab file. Maybe you can get rid of X1, model with X2, X3, X4, and then maybe in the next class we can discuss how the model performance had been. Okay. And what
So
is this?
how do
Hmm.
we access that? We will get the link to how
Yes,
will
yes.
we get that?
I will make sure you will get we will get through email or somehow we will upload it on the course portal. I will make sure that you get this file.
Okay.
Okay. Next is normality of residual. What does this mean? What is a residual?
The error that you get,
Difference.
the
Okay,
difference
And
between the y
actual
actual
error.
and the y predict.
okay. This is our actual test data and this is our predictions. So the difference between y test and y predict is stored as residuals. And if I plot my residual, how does it look?
Normal distribution.
So it looks like a normal
No,
distribution. Now, how do you check whether it is a normal distribution or not?
it's a More of like symmetric curve
Sorry, yeah,
in the center. More of like
okay.
a symmetric curve peaking at the center.
Okay, so you through visual inspection we can say it is near normally distributed, but you have had training on distributions.
This mean, mode, and median should be equal.
Yeah,
Yeah,
those are certain ways to
centered.
ensure. You, if you remember, Malolan had a session on chi-square goodness
Yeah,
of fit.
chi-square goodness of fit. Yes,
Yeah.
Goodness of it.
So if you want to be very sure about the normality of residuals, what do? You go for chi-square
chi-square.
goodness of fit, and then check for normality of residuals. All right.
Okay.
What is the next
Mhm.
one? What is this? Have you heard of this particular term?
No.
No.
Homoscedasticity. Okay, so here what I'm doing is I'm plotting my predictions versus residuals. You see any pattern here, or is it random?
Look random, sir.
Okay, so
Random.
okay, it looks random. Let's see what heteroscedasticity means. Okay, so here, do you see a bell-shaped pattern? It is similar to a speaker shape.
Hmm.
Yes, sir.
Whereas, whereas
Yes.
here it is more of a random. It is more of random. And remember, this has been plotted with x1 included. So maybe if you remove x1 and then replot this, it will look it might look more random. All right. So you also check for homoscedasticity. Then finally, what is this?
So what is the purpose of plotting this thing?
So what will happen if you're okay? The valid question. What is the purpose of checking for homoscedasticity? Just a second. Okay, let me reshare. Where is my screen? Is my screen visible
No.
now?
Yes.
Okay. So you see whether you have any particular pattern. Is there some confounding variable in your model that is affecting the randomness? So when there is no evident pattern similar to this, right? It means there is homoscedasticity, and it actually goes hand in hand with the assumptions of linear regression, where there is no confounding effect. Right? If you see, these are typical patterns. So here there is no pattern, whereas here, do you see a pattern?
So what we
They
can
are
conclude from this, like if we have homosced, whatever it is, and then we have hetero. So
okay.
what actually we are gaining from this graph? Like what interpretation we are making out of it?
Um the standard
Like,
deviations, the errors are not uniform. I mean, they have a particular pattern. Your errors, they are
mm,
having a particular pattern which
okay,
violates the assumptions of linear regression. Your predictions
should
are,
be
it
should
is
be
affected
random.
by, it should be random, not your predictions. Your errors should be random. So that
Okay.
is what happens when you even plot your residuals. It is normally distributed. It is completely random. It doesn't center around some particular value. So it
Okay,
is
so
randomly distributed.
our motto should be that the residual should be random. They should not follow any distribution
Any particular pattern, yes.
pattern. Okay.
Okay. So next comes this concept called autocorrelation. So we use a plot called ACF, autocorrelation function. So what do you see anything here? So there is a blue region. Is any point coming out of this blue region?
No, one point only, the
Yes,
starting
only
one.
one point. So here, this autocorrelation is this kind of autocorrelation is typically seen in time series data. For example, uh, today's stock price was high. Will tomorrow's stock price be high? Will today's
No.
value
No.
affect tomorrow's value? Today you had a high stock price. So today being high, will it have an effect on tomorrow's price?
No.
Yes.
No.
Yes, definitely. Similarly, petrol price, gold price. So the past values have a tendency to affect the future values. Today it rained. Is there a chance of raining tomorrow? Is there a chance of getting rain tomorrow? You can't say no,
Yeah, correct.
right? So today gold price was high. So tomorrow it might be high because today it was high. Given that today's gold price was high, there is a high chance that tomorrow's price will also be high. Okay. And why do you see one here? That is because the correlation with itself is one. Whereas when this point is going above this blue region, which is the blue region, when you have these lag variables going out of the blue region, it means there is autocorrelation, and you have to treat it as a time, you have to treat it properly. It will violate the assumptions of linear regression because linear regression has this assumption of independence
And
that
also that the errors are centered around zero.
it is centered
That's
around
why.
zero. Yes. So here, if I plot the mean of the residuals, is it near zero?
Mm.
So
Hmm.
it is what distribution is that when your mean is
Standard
zero,
normal. Standard
and
normal.
what should be the deviation?
1.
Okay,
One.
yeah, good. So these are some of the assumptions that you need to ensure for validating your linear regression model.
Okay, so if in autocorrelation, if the points are going beyond this blue region, that means we need to
Yeah.
validate.
Okay. Yes. So it means that past values are affecting future predictions. So
Okay.
therefore, if you include some parameters like date, time, what else? Day of the week, month, year, week, whatever, weekday, week. So these kind of temporal features, they become very important in the model, and you don't want them in linear regression. Maybe if you're working with time series data, these are more important. But for linear regression, you have an assumption that the values are independent, and you don't want autocorrelation. All right.
Sorry, sir. Could you repeat the point? Which one is?
Which part you want me to repeat?
Is like in comparison with time series you were saying, no?
Mm. So what is time series and what is cross-sectional data? Somehow my writing pad is not working. So next week I'll make sure that I will write and show you certain things. Uh, so we
Sir,
have two types of data. One is called,
sir,
okay, first let me finish this, sir. Then I'll come back to your question. So we have two types of data. One is called cross-sectional data, and other one is called time series data. What is the difference between cross-sectional and time series?
So
Cross-sectional data
for
taken at the
time
same
series,
time at different locations.
Mm,
for
not
time
location.
series, for time series, the future values depend on the past values.
And data is collected over regular intervals. For example, the sales volume, every month on month, you collect the data, right? If you want to do stock prediction, and if you want to call it as a time series, you collect daily stock values and then make the stock price prediction. It is collected over a regular interval of time. It could be daily, it could be weekly, it could be bi-monthly, monthly, and so on. So the difference between December to November, November to December is same as January to February. So January to February is 1 month data. Similarly, the difference between November to December is again 1 month. So you are collecting data over a fixed interval of time. And as you rightly mentioned, the past values affect future value. Whereas cross-sectional data, you don't have to necessarily collect it over a fixed interval of time. right? So here you have those independent. If you model this cross-sectional data as linear regression, you'll have to check for homoscedasticity, normality, autocorrelation, homoscedasticity, and so on and so forth. Whereas when you deal with time series data, you look for certain more things. Have you done time series in some courses?
Not yet.
Not yet. Okay,
No,
you will do
sir.
that. In the coming days, you're going to do it. Okay. So what I will do, I will share this particular file with you, and you can play with this data. And the next thing I'm going to do is slightly different. So what I will do is I'm not going to record that session because it is completely out of scope. I will stop the recording and the live stream now, and then go to that deployment thing because it is not at all required in the business analytics course. Just going to do it for the fun of doing it. That's all. So any questions on this? Shall we move on to the next one?
So we need to, the things that you have mentioned, we need to check this for the linear equation.
Only
If
for linear regression. Yes.
if we are getting this, then we can say our model is valid,
Yeah.
right?
Yes, your model is valid.
Okay. Okay. And
Sir,
also,
what
can we
is
ask?
Yes.
Okay.
One by one.
Okay. So can we ask a question regarding the graded assignment too?
Can you?
Can we ask a question regarding the graded assignment too? No, we are not going to actually ask a solution, but we just
Hmm.
have a doubt.
Yeah. Please.
Yeah. So, like we have been given two column price and sales, and the doubt is in which one to decide as a target. Like, if
Okay.
I'm
So I am not going to give you the answer directly, but I even saw Utkarsh responding to that question on discourse.
okay,
But
okay.
you need to tell me. We have seen those concepts on demand response curve. So there
Mm,
we model demand as a function of price.
mm,
Do you agree?
yeah.
When you increase price, what happens to the demand?
Demand decreases.
When you decrease the price, what happens to the demand?
When you
Decrease price, what happens to the demand?
demand increases,
So what is the output variable? What is the input variable?
now the input variable will be price,
Yeah.
and demand is changing.
Yes. All right.
Yeah.
Okay.
Okay.
Sir, Shukla sir, Purnendu
Hmm.
Shukla. Yes, sir.
Sir, what is homoscedasticity? Whatever you mentioned.
Okay. Okay. It is going to be a
Homoscedasticity, you said, no?
yes.
Scadicity.
So you are going to check the variance of our target variable. So is it same everywhere or is it slightly different? That's all. So it's a statistical term. Any Google you do, you can understand it better. Shouldn't be a problem. Let me also do that. Once I stop the live streaming, I will show you what it is. So I'll stop the live streaming and the recording for now, so that we could do something unusual. Okay, I'll stop the streaming. I will also stop the recording.
Sir, I also have a small doubt
Yes.
from